Hopefully with this configuration, the output is a scaled up version of the sum of all of the inputs here, or even better, I individually scale each input by some value and then add them in a summing matter, and this is my output signal. Hopefully, we shall see. Now, to analyze this circuit, I can say that this equation holds true. Alright, V out is A0 times V plus minus V minus, point X here. Some will say it's with a virtual ground, and it is in an ideal op-amp. But if A0 is not very large, I cannot say that Vx is a virtual ground, that Vx is 0. What I'm going to say is I'm going to take the general case where A0 is not very large, and I'm going to say that, well, V plus must be 0 and V minus must be Vx, this Vx here. Alright, hopefully you understand why. And this equation reduces to this. Now, I'm going to say that there are a couple of currents flowing, all of them into this node X. And if I take a KCL here, since all of this must sum to a common current, I'll name this IF. This current can't really flow inside the op-amp, so it has to flow like this. This is called RF, this is called IF because this is the feedback, alright? Therefore, the current here must be nothing but from the Ohm's law, alright? This is taken from the Ohm's law. There must be V1 minus Vx over R1, V2 minus Vx over R2, etc. Alright? And this must all be equal to IF, which is equal to Vx minus Vout over Rf. Now, if I separate all these things like this, and I put Vx here as a common factor on this side of the equation along with Vout, I can take this equation from before and replace Vx and eliminate it from my equation with Vout over A0 with a minus in front. Now I have nothing but a Vout and all of the common quantities I know, V1, V2, V3, and the resistances, and A0. And therefore, I can finally have my equation, which is Vout is equal to something, alright, multiplied by something V1 plus something V2 plus something V3. Hopefully, you see that and you understand that now we have created what we wanted in the beginning. We have an output which is a scaled V1 plus a scaled V2 plus a scaled V3, alright, multiplied by something like this, which will be multiplied individually with all of my components here. A very general case where A0 is not very, very large. On to making some observations here. I'll say, alright, what if A0 is infinite? What if it is very large? In that case, this whole thing reduces 0. A0 is infinite, so this is very large. And 1 over A0 here, again, this is very large, so this is 0. And we have at the denominator here 1 over Rf. So we have 1 over Rf multiplied by Vx. What is 1 over 1 over Rf? It is nothing but Rf here, alright? V out is minus Rf times 1 over 1 over 1, etc. We see it here, which is nothing but, again, the output which is a scaled V1 plus scaled V2 plus scaled V3 with a different scaling factor. I have absolute control over these values. I can change them by changing these resistances as I please, as I want for my applications. Now, if A0 again is very large, but I choose to have resistances which are the same, R1, R2, R3 has the same value, I'll name this Rin from the inputs, right? You can name this however you want. Then the output must be nothing but minus Rf over Ri. You see, this is a common factor. It goes outside. It is V out is minus Rf over Ri times V1 plus V2 plus V3. This is again what I wanted again from the beginning. The output is a common scaling factor of V1 plus V2 plus V3 and whatever else signal I have. Now, another case. What if A0 is not very large, it's not infinite, and R1 and R2 and R3 are equal to I? And then I can prove from this equation that the output is going to be a common scaling factor of the V1 plus V2 plus V3. Hopefully you can see why. The math is very simple here, all right? 1 over Y. And this whole thing reduces to this, which, by the way, if A0 is infinite, this whole thing reduces to this way that we had before, right? You can see it why here. And you can prove this very easily. I will not show the proof here. You can prove this if you want. Now, to test our knowledge, let's look at this exercise in which we are asked to perform this mathematical operation. We want the output to be equal to minus the front 2 times x plus 4 times y. All right. We are given an op-amp with A0 equals 10, not very large, all right, notably. So we'll keep this in mind. This is the equation. I put this here, but we have proven to be the general one. Again, now I will pick an RF of 100 ohms. I can buy this very cheaply. It's very easy to find. And it's a very reasonable value for the feedback resistor. And I take this equation. Now I don't have a third signal, obviously. I have 2 signals here. And I replace all my known values here, or my known quantities. I replace A0, I replace RF. All right, and I have this equation here. Now, I'd say that if this is multiplied by this and this is multiplied by this, I want this to be equal to 2, and I want this to be equal to 4. And now this is nothing but a system of 2 unknowns with 2 equations, which can be solved very, very easily. And after solving this, we have an R1 is equal to 18.2, about 18.2 ohms, and R2 is 9.1 ohms. Very, very logical values. These resistances can be built very easily. I can buy a resistance of 9 ohms and a resistance of 0.1 ohms and put them in series. All right, I can create these resistances very, very, very easily and very cheaply. So I see that the resistance I picked for the feedback of 100 ohms can create this output, the desired output, by picking some smaller resistances here for R1 and R2 and creating this mathematical operation. And that's it. Very, very cheaply, very, very, very easily, with very, very cheap, very, very logical values, I have the desired outcome. Now, when I was cooking up this exercise for this video, I stumbled upon an interesting case. Well, can we, using the same op-amp, create this mathematical operation where instead of 2 times x plus 4 times y, we had something larger. It had 5 times x and 7 times y. All right? Can the output be something like this using this op-amp? The answer is no. All right, the answer is no. We cannot really do this. So there's a limit to how much we can scale this with this, depending on the A0 of the op-amp. But why? Why can we not do something like this? It turns out that when this plus this is more or equal to this operation is impossible. Why? Why? I leave this up to you. You can prove this mathematically. I will not show the proof here since this is outside the scope of this video, but you can prove it and you can tell me all about the proof in the comments below. I I will be very proud if you actually manage to prove this. It's not very hard, but it's going to be very interesting. All right, that was it for today. Check out my op-amp playlist over here and subscribe to the channel for more electronics videos. Study well and take care.